Hi guys, welcome to our third in our four-part series on NMR spectroscopy. And today we're going to be talking about proton NMR applications. So you'll get a feel of how you will be able to use the knowledge that we would have gained in the previous two lectures. All right, so we have to start off with a little bit of a revision. So here we mentioned this last time, but just to go over it again, or spin-spin coupling splitting patterns. All right, so as we mentioned the last time, the number of equivalent protons to which hydrogen is coupled, and that varies. So we just have 1 to 6 here, and the appearance of the doublet. So when it's 1 equivalent protons coupled, then we get a doublet. When it's 2, we get a triplet. When it's 3, quartet, etc. And in terms of how these peaks look, we know that the doublet has a 1-to-1 ratio, and you can recheck that or revisit that lecture to look at the images, the types of lines that we're talking about here. All right, so continuing on our splitting pattern, right? So again, if we have these two equivalent hydrogens, right, and we don't have any neighboring hydrogens on our neighboring carbon, then this gives a singlet. So no neighbor gives a singlet. N plus 1 therefore is equal to 1 because n is 0. The area or the integration under that peak would be equal to 2 because it represents 2 protons. All right, so when we have one neighbor, as is seen here, so our 2 equivalent hydrogens that are in the same environment, and they'll be split by a neighboring hydrogen. So we look at this carbon, they're both attached to this carbon. So the neighboring or adjacent carbon has 1 hydrogen attached. If it has 1 neighbor, that means that n is equal to 1. And therefore n plus 1 is equal to 2. And the area under that peak under that doublet would be 2 because it represents 2 hydrogens, right? So 2, once we get 2, that means we have a doublet. Once we get 1, that's a singlet. All right, so let's look at our triplet. So how do we get a triplet? All right, so the proton that is circled, right, that is the proton of interest this time, right? So previously, our protons of interest have been these two, the same methylene that was circled. In this case, the proton of interest is this one that is circled, right? This methylene that is circled. Not methylene, methane, because it's a CH. So methylene is a CH2, methane is a CH. All right, so this is the proton of interest. So it is attached to a carbon that has an adjacent carbon that has 2 protons attached. So that means that n is equal to 2, and therefore n plus 1 is equal to 3, and 3 means that we have a triplet, right? And so the area under this curve or this triplet, however, would be 1 because it only represents this proton here. All right, so in this case now we have 6 neighbors, right? So this is a proton of interest. It's attached to a carbon that has two adjacent carbons, and both have 3 hydrogens each. So that gives us a total of 6. So our n therefore is 6. 6 plus 1 is equal to 7. The area under that curve would be 1 because it represents only one proton. And we would get a septet. And here, the protons, so the same molecule, but we're looking at the protons of interest here. And in this case, each methyl has one neighboring proton, right? So this is a methyl, and all 3 hydrogens are equivalent. They're in the same electronic environment. And our neighboring carbon here has 1 proton attached to it. So therefore, n is equal to 1. 1 plus 1 is equal to 2. The area under this peak, under this doublet, therefore would be 6, because it would be representative of 6 protons, because these 2 methyls, even though they are, on the other side, they are in the same electronic environment. Because if we draw an imaginary line, right, and we're going to look at this later on, right? So if we see that we have a line of symmetry, so if we fold the molecule along that line, I know it's not a straight line, but just imagine that it is straight. If we fold the molecule along that line, we'll see that we have a line of symmetry. If we have a line of symmetry, that means that both methyls are in the same electronic environment. All right, so let's consider the spectrum for 1,1,2-trichloroethane. All right, so having used, the knowledge that we have garnered over the past few weeks, we should be able to decipher which peak is what just by the multiplicities. That is whether or not it's singlet, doublet, triplet, etc. All right, so for our HB, right, that is hydrogen that's labeled B, right, we can therefore surmise that we have 2, N would be equal to 2 here because we have 2 neighboring hydrogens. And so we would expect what? What would we expect? If n is 2, then n plus 1 would be 3, right? And if we get 3, that means we would have a triplet, as is seen here. And then for HA, both of them are in the same electronic environment, right? And they have 1 neighboring proton in the form of HB, and so n would be equal to 1, and so we would get a doublet for HA. So without even looking at the chemical shifts, we would be able to assign or protons just by looking at the multiplicity. So just in case this might be confusing, this is how the spectrum looks, right? And this is just a zoom in on HA. So HA, if you zoom in on it, it will look like this. And the value that we read is the midpoint, right? So somewhere here, that's the value that we would record as our chemical shift. And the same for this, the midpoint here, that is the value that we would record as our chemical shift. And again, this is the same thing as this. This is just a zoom in of this little portion from 5.65 to 5.58. All right, so the spin-spin coupling effect can be quantified using coupling constant, which is abbreviated with the capital letter J that I'm sure we have met already. The coupling constant J is the difference expressed in hertz between two adjacent subpeaks in a split signal. Now for our doublet in the 1,1,2 trichloroethane spectrum, for example, the two subpeaks are separated by 6.1 hertz, and thus we write JAB is equal to 6.1. So that J value is literally the difference in hertz between the two peaks here, and in fact when you subtract the two values you get 6.1 hertz. And this is an important attribute that we can get from the spectrum, because if the splitting works out to be the same, then we can surmise that these protons are adjacent to each other. So anytime you see any data and we can immediately pick up our similar J values, then we can know for a fact that these sets of protons are adjacent to each other because they have the same J value, right? So how we calculate the J value for a triplet is the difference between in hertz between the middle peak and this one, or the middle peak and this one. All right, so you should get the same value if the protons are coupled to each other. All right, so use of deuterium in NMR. So although deuterium has a nuclear spin, deuterium NMR and proton NMR require different operating frequencies. So deuterium NMR absorptions are not detected under the conditions used for proton NMR. The coupling constants for proton deuterium splitting are very small, and so solvents used in NMR spectroscopy must either be devoid of protons, or their protons must not have NMR absorptions that obscure the sample absorptions. And one compound that comes to mind, for example, would be a reference compound, where we can set it as a reference because generally it does not interfere with our sample peaks, and that is, do you guys remember what that is? TMS. All right, so the idea here, guys, is that deuterium, yes, it has spin, but based on the proton NMR operating frequencies, we're not able to observe those peaks. And that is why we're able to use them as solvents. So these are some of the common solvents used in NMR. And the properties of them generally are that, one, they are non-viscous. They should dissolve the analyte, and they should not absorb within the spectral range of the sample being analyzed, and that makes sense because you want to see your sample peak. And perhaps most importantly, they should be aprotic, that is, they do not contain protons, because the idea here is that you want to run a proton spectrum. So if you have a solvent that you use to dissolve your sample, you don't want to see any peaks associated with your solvent. All right, so I suppose the most commonly used solvent would be deuterated chloroform, which we have met before. And on the proton spectrum, you will see a peak at 7.26 ppm. And we have seen that already. In addition to deuterated chloroform, there is D2O, and we did mention that already. And deuterated acetone, DMSO, that's deuterated dimethyl sulfoxide, and deuterated methanol, right? So all of these solvents are commonly used, but I suppose chloroform would be the most commonly used solvent to dissolve your sample so that you can see your sample peaks. So we're going a bit into the application side of things now. So the NMR of alcohols and amines, so we mentioned this already, so this is just revision. The chemical shift of the hydroxyl proton in an alcohol depends on the degree to which the alcohol is involved in hydrogen bonding under the conditions that the spectrum is determined. So the presence of water, acid, or base causes a collapse of the hydroxyl resonance to a single line, and you will for the OH hydrogen you probably see like a broad singlet, as you know how we characterize it. But we're seeing here to a single line or a single peak, and obliterates all coupling associated with this proton. So for hydroxyls, you won't see it as a doublet or a triplet, etc. You'll see it as just one peak. This effect is caused by a phenomenon called chemical exchange. So this type of behavior is quite general for alcohols. So it's not just alcohols, it's amines and other compounds with a proton bonded to an electronegative atom. So we met those already. So sulfur, hydrogen bonded to, anything that's electronegative, that will give us a single peak and there will be no coupling. All right, so continuing on that. So rapidly exchanging protons do not show spin-spin splitting with neighboring protons. Acid and base catalyze this exchange reaction, accelerating it enough that splitting is no longer observed. The assignment of the hydroxyl proton can be confirmed by adding a drop of D2O to the NMR sample tube, shaking, and then taking the spectra. So we saw this already. We're going to see it again. The hydroxyl protons rapidly exchange with the protons of the D2O to form OD groups on the alcohol and thus becomes invisible to the NMR. So the idea here, guys, is that if you're uncertain as to whether or not you have an exchangeable proton, this is a simple experiment that you can do to check if you have such an exchangeable proton. And this is a repeat slide, but repetition is good, right? So here we have methanol in deuterated chloroform with TMS, and this is what the spectrum looks like. So this is our TMS peak, this is our methoxy peak. These protons resonate at about 3.42, and we have our hydroxyl hydrogen, which is about 3.97, and we're not seeing our chloroform peak, which we said we would see at about 7.26. All right, so methanol in deuterated chloroform with TMS, that's what we have above. And if we add 1 drop of D2O, shake and then rerun the spectrum, guess what? Our hydroxyl group disappears, and therefore, as we said on this slide, the hydroxyl proton rapidly exchanges with those D2O protons, and they form OD groups to the alcohol and thus become invisible to the NMR. So if you saw this when you ran the spectrum initially and you want to check if this is an exchangeable proton, you just add a couple drops or one drop of D2O, and if that peak disappears, you have pretty much confirmed that you have an exchangeable proton. And as we said, NMR signal for deuterium not observed with an instrument set up for proton NMR. We can detect these types of exchangeable hydrogens. That is when the hydrogen is bonded to oxygen, nitrogen, or sulfur using this technique. All right, so as I said, this lecture is mainly applications, so let's see if we can get into them. All right, so Proton NMR Example 1. So a question that you might see is predict the spectrum. So you have this structure, right? So now you have all this new knowledge in terms of functional groups and, you know, where they appear, and now you know how, you know, the protons would resonate differently based on their different electronic environments, right? So your knowledge of you know how electronegative groups influences the chemical shift, and your knowledge of the table, right, of the, you know, with our chemical shifts should help you to predict a spectrum like this. All right, so let's work through this, right? And also I didn't mention the multiplicity, so that's an important factor as well, right? So this is the compound that I would have asked you to predict the spectrum for. So if you pause the video and took some time to, you know, just posit something, then, you know, you may have said to yourself that this proton is in a different, or this set of protons are in a different electronic environment than this, and this is in a different electronic environment than this, right? So we have a CH3 here, which is a methyl. We have a CH2 here, which is a methylene, and we have another CH3 or a methyl here. So if you literally just drew 3 different peaks, not even sure where they are, you would have been onto something, because at least you know that you have 3 different types of protons, right? So the other thing that we want to examine is the multiplicity. So looking at this, you know, based on our experience so far, you would have perhaps expected this set of protons to be singlet, seeing that they don't have a neighboring proton. And then for these protons here, these methylenes, we would expect them to be quartet, seeing that they have 3 + 1 and +1 rule. So we'd have a quartet for these methylenes. And then for this methyl, we would expect the multiplicity to be 2 + 1, which should be 3, a triplet, right? So just by doing all of that, you know, and seeing the spectrum, we would, if we saw the spectrum, it would be easy for us to assign which proton we're talking about. But one thing that we haven't done so far is to give an approximate chemical shift, right? So at your stage, eventually you'll be expected to predict a chemical shift. So that means that yes, you won't be able to predict the exact number, but close enough, right? So because it's a range for certain types of functional groups, right? So for example, this proton, which is the furthest, is methyl protons. These methyl protons, which is the furthest from our most electronegative atom in the form of oxygen, it's farthest. So it's 1, 2, 3, 4 bonds away. And we would expect this set of protons to be the most shielded set of protons. And if they're the most shielded, then we expect them to be in this 0.9 to 1 point something region, right? And then the other sets of protons, which are basically equal distance away from our carbonyl here, which is our ketone carbonyl, oxygen, would be in this range. So we have our singlet, which is 2 point something, and our quartet, which is also 2 point something. So they are in a similar range, right? All right, so we have already gone through the assignment, right? And also one thing we didn't even mention was the integration, right? So the area under the peak would also, confirm which peak is associated with which groups of carbon. So we did say that this methyl that is in red, that it would be a singlet because it doesn't have any neighboring protons. And we did say that the blue methyls here would be a quartet. And we did say that the terminal methyl here would be the terminal set of protons here would be a triplet. And that is literally how we would predict our spectrum and how we would assign our spectrum, right? So you can't just predict it. You have to say, you have to say which peak corresponds to which set of protons. All right, so let's try another example, and we have a number of them coming up. So Proton NMR Example 2, predict the spectrum. So the first thing that you want to do is to count your protons, count the number of electronic environments that you have, right? And then you look at your electronegative elements, and just to try to estimate, our most shielded and our most de-shielded protons by virtue of proximity to our electronegative elements, right? And then you look at, your neighboring protons, you look at multiplicity, and so you want to look at all of these things and propose something. All right, so if you propose something like this, you're definitely onto something, right? So let's look at this, and the other slide has the respective assignment. So on this slide, let's just count the number of electronic environments. So based on the spectrum, it has 1, 2, 3, 4, 5 different environments, and so you should at least, that is the minimum expectation that I have of you up to this point, to be able to identify the electronic environment. And the other thing that I expect that you'll be able to do at this point, at least the multiplicities. So remembering the chemical shifts, that skill will take a little bit more time investment on your part, and just studying the table so that you can get more, and the more examples that you do, the more experience that you get, and the better you will be at predicting the chemical shifts. But before the chemical shift, the skills that are necessary are predicting the electronic environment and the predicting the multiplicity. All right, so here, we have one chemical environment, electronic environment. We have 2, we have 3, 4, and 5, right? So there is a hydrogen here. So that's one environment, 2, 3, 4, 5. So 1, 2, 3, 4, 5, right? So even looking at it, you should be able to say, for example, which peaks do you expect to be de-shielded, and which peaks do you expect to be the most shielded, right? And at this point, you should be able to come up with that. All right, so let's look at the assignment, right? So here, the most de-shielded proton set of proton would be the methylene attached to the electronegative chlorine, which is here, and it's a triplet because it has 2 neighboring protons. And another peak, and it's at 3 point, what is this, maybe 6, 7, right? 7-ish. All right, that's the midpoint here. So bring it all the way down. So this is 3.5 and 4. So it's somewhere in the middle here. All right, so going from this end, the next up is our other set of protons that are attached to an electronegative oxygen, right? And it is clearly a singlet, and we would expect it to be a singlet because there is the protons are attached to a carbon that is attached to an oxygen, right? And so we would expect it to be a singlet, and for it to be de-shielded as well because it is in close proximity to an electronegative atom. And then we have our peak here. So our methylene, right, we have 3, 4, 5, right? 5 plus 1 would be equal to 6, right? So going back to our splitting pattern here, if we have 6, and let's just count how many neighboring protons do we have. Is it 5 or 6? 5 or 6? All right, so let's count it properly. So we have 2 here, 3 plus 2, that's equal to 5. So here we have 5 neighboring protons, right? So that means that we should have a sextet, which means that we should have 1, 2, 3, 4, 5, 6 lines. So let's count and see if we do in fact have 6 lines. All right, so 1, 2, 3, 4, 5, 6, right? So I know that these 2 peaks are very, not intense, right? But we do have our sextet here. And then finally, the more shielded protons are, I'm sure you would have guessed it, or methylene here, which is a couple, bonds away from our electronegative atoms, right? And so that resonates at about, what is it, 1.5 is would be here, so 1.6 ish, right? And that's for these methylenes here, and of course they are a quartet, right? Because we have two, well, let's use this one. So we have 2 plus 1, 3, and 3 plus 1 is equal to 4, so we have a quartet here. And then finally we have our methyl, right? So we only have one neighboring proton, so we have a doublet for this methyl here, right? So I hope we're gonna do a number of examples, so this will add to your experience, and the more you add to your experience, the more that you will get comfortable with the assignments, right? So far, we should be getting the shielding, de-shielding type of information, the chemical shift information, what else? All of, clearly it's a lot of things that we have to think about here. All right, so let's look at another example that is a little different from what we have been looking at so far. So here we have an aromatic compound, right? So this one is a little bit more challenging. We have an aromatic compound, and we have some substituents to that benzene, as we probably would have known benzene, that is substituted in the para arrangement. So are you now able to predict this spectrum? Maybe yes, maybe no. All right, so what let's, and I hope you have your chart, your proton NMR chart handy, right? Because what you need to be doing is looking out for your different functional groups and looking at where the chemical shift for them, where you would expect them to be, right? So this is important in your practice. All right, so this is what the spectrum looked like. All right, so if you had, if you counted your different electronic environments correctly, kudos to you, right? So we're going to look at the assignment in the other slide, but just to count our electronic environments. So we have one electronic environment here. There's no proton here because it's a quaternary carbon. There's no proton here, so we have 2 protons here, 2 protons here, here and here respectively. We have this proton here, and we have these protons here. All right, so how many electronic environments do you see? All right, so we see 1, 2, 3, 4, 5. So is it 1, 2, 3, 4, 5? All right. So what we're looking at here again, we're looking at our line of symmetry. So within our aromatic compound, we have to use and look for any line of symmetry, right? So in other words, if we fold or just the aromatic part, just the benzene ring portion, if we fold it in two, right, we would have this proton being equivalent to this proton, and we'd have this proton being equivalent to that proton, right? So that is literally what we're seeing here. So these protons are equivalent, and we're seeing that these protons are equivalent. That is essentially what we're seeing by virtue of, the fact that we have a line of symmetry. All right, so if that's the case, then we have all of these are in the same environment, right? Then these would be 2, then we will have 3, clearly this would be 4, and then these methyls, terminal methyls, would be in the same environment as well. All right, so let's look at the multiplicities, right? So here we see that we have 2 doublets, right? So clearly this proton has only one neighboring proton, sorry, and so it would be a doublet. So each of these would be doublets. This would be a singlet. So essentially everything else would be a singlet, right? And this is our assignment. So essentially, right, or methyls or tert butyl portion, these methyls would be the most shielded, right? And or methyls here as well would be shielded as well, right? And relatively shielded, right, in the shielded portion. Then our aromatic protons, and if we look at our table, we would notice that we would expect them to be in the 6 to 7 region, depending on, of course, what is attached to them. So our aromatic protons, so these protons that are closest to the tert butyl portion would be more shielded than the other protons seen here, right? And here we have our alkene hydrogen. So typically would expect that proton to be in the 5 to early 6 chemical shift, and clearly that would depend on the chemical environment, whether or not it's attached to something that is electronegative or just pulling electrons to itself. So yeah, that's basically it. So we have our shielded protons and our deshielded protons, and we're able to assign them based on their multiplicities, and by virtue of knowing the chemical shift of our aromatic protons as well as our olefinic or alkene protons. All right, so moving on to another example. The 2 spectra below are of phenol and benzaldehyde. Assign them. So phenol would be our benzene ring with a hydroxyl substituent, while our benzaldehyde would be our benzene ring with an aldehyde attached to it, right? So I mean, I could have flipped it anyway. And in any case, one hydrogen is substituted for an aldehyde, while in the case of the phenol, one of the hydrogens is substituted for a hydroxyl group, right? So you have two spectra here, and of course what we said is the singular spectrum, plural spectra, which is which. Okay, so again, you might want to draw for your table, which you should be trying to remember, and you want to be looking for the chemical shift of aldehydes and the chemical shift of the hydroxyls, right? And I think that will be the most defining thing, right? Or information, because clearly, in the aromatic portions, right? And we may be able to find, the chemical shifts for the phenol aromatic protons as opposed to the benzaldehyde aromatic protons, because clearly, sorry, am I giving it away? But either way, the arrangement of the peaks looks the same, but for one, the peaks are between 7 and 8, more towards the 8 in terms of chemical shift, and the other is more shielded, right? So one is more upfield, one is more downfield. So that is an important thing that you need to pick up on, right? And you also need to pick up on the similarities in terms of the arrangement of the peaks are pretty much the same. And then finally, the only distinguishing feature is, the hydroxyl and the aldehyde proton. So you want to look in your chart to distinguish, where does the aldehyde proton resonate, right? So if you checked your chart, then you probably would have guessed that this is your benzaldehyde, based on where the how the peak looks, the shape, it's sharp, and how the peak looks, as well as the fact that it occurs in the 9 to 10 region. While, as we know, with the hydroxyl peak, it kind of varies, but it's more on the broad singlet type of spectrum. And yes, so we know for a hydroxyl peak that it varies, right? So we don't know exactly where it will resonate, so we can't really bank on that. But the shape of it is important. It's usually a broad singlet as compared to this aldehyde peak, which is very sharp. And our integrations are basically the same, because our integration suggests that we have 5 protons here and 1 here. They're basically the same, giving us the same information. So that wouldn't be useful knowledge to decipher. All right, so another example: for the spectrum below, choose between the alternative compounds, give your reasons. So here we have 2 possibilities for assignment that goes along with this spectrum. And so essentially you want to look at your spectrum, right? So, and your compounds, the structure. So we have 2 hydroxyl protons here, so that won't necessarily help us, right? We have our integration. Well, we have a methylene here, a methylene here, a methyl here, and a methyl here, right? So what would probably help you guys out here, I think, would be the multiplicity, right? What would you expect the multiplicity of these protons to be? And what would you expect them to be here? What would you expect them to be here? And what would you expect them to be here? Right? I think that would be the distinguishing feature for, one versus the other. because here we have CH2, that's a quartet, right? Clearly. And then we have a CH3 here, that's a triplet, right? So clearly this structure is a better fit for the data than this one, that these protons, they don't have any neighboring protons, so they would not be quartets and triplets. So again, we're getting some more experience. Example 6. So for the spectrum below, that should have been choose between the alternative compounds. Give your reasons. All right, so here, we have two similar compounds. We have a proton spectrum, right? And, you want, this one is a little bit, perhaps a little bit more tricky than the other, because you want to look at the size of the peaks, right? So clearly we have some aromatic protons here. We have a smaller peak, which would possibly correlate to, or well, either hydroxyl, just by virtue of, the area under it should be the smallest for both, right? Because it would represent one hydrogen. So we kind of would expect this peak to be that of the hydroxyl, and these peaks here should be that of the aromatic protons. So here, we have to think. So this peak at 4.5 something would have to be the methyl here, or the methylene here, right? So what would you say? Based on the fact that the methylene is in such a close proximity to our hydroxyl, I think we would expect that peak, or those methylene, protons, would be quite de-shielded and in the 4.5 region. And so I think that would be or benzyl, the spectrum for or benzyl alcohol. And then, or another example here, example 7, and it's the last one. Propose a plausible structure for the compound whose proton NMR spectrum is shown below. So you're given this molecular formula, right? And you're given the spectrum in this case, and you're asked to propose the structure, a plausible structure for the compound based on that information. All right, so one thing that we see here, and this should be familiar to something we have seen before, which would be two doublets, right? So you might want to go back and look which peak, which compound did we see two doublets in the aromatic region, and how was that molecule arranged, right? And then here we have based on the integration as well, we have 2 to 3. So it could possibly be, 2 hydrogens in the same environment, 2 hydrogens in the same environment, 3 hydrogens in the same environment. And of course, guys, we have a bromine in the structure. So by virtue of the fact that we have some aromatic protons, and we know that because we have the 2 doublets in the 6 to 6, 7, 8 region, right? And the fact that we have two doublets in that region suggests that we have a line of symmetry in, and so we have a para arrangement, right? So I'm just going to go ahead and draw something. So we have a bromine for sure, and based on that, the fact that we have a what it looks like a CH3 in the almost 2.5 region, I'm just going to go ahead and draw something, right? But the idea here, guys, is that you may have draft 1, draft 2, draft 3, but at the end of the day, all of the data should make sense and you should be able to come up with something plausible. So when you come up with a structure, then you need to count to ensure that the data matches up. So the structure that I have drawn on the screen, is it C787Br? So it has 7 hydrogens for sure. It has 7 carbons for sure, and it has a bromine. So that checks, right? Then you want to check to see, will the methyl be a singlet? Which I think it would. It doesn't have a neighboring proton. And the 2 doublets, we know based on our previous experience with those 2 doublets in that region that these hydrogens would be the same and these hydrogens would be the same, right? So in this case, you're just asked to draw the structure. So this is all you're doing, just draw it. Okay, so again, this is an example for the mere purpose of us increasing our knowledge, increasing our experience. All right, so double bond equivalence or degrees of unsaturation. I'm sure you thought we were perhaps finished with the knowledge, but another thing that will become important to us is DBE, which is double bond equivalence or degrees of unsaturation. So here, this formula we need to know, right? So the formula is 1 plus N4 minus N1 minus N3 divided by 2. So what is N4? N4 is the number of tetravalent atoms in the molecular formula. And N1 is the number of monovalent atoms in the molecular formula. And N3 is the number of trivalent atoms in the molecular formula. So for our organic purposes, and we will be using mostly carbon, hydrogen, nitrogen, for example, what you will see is that the tetravalent atom that we will most commonly or perhaps only be referring to would be carbon. So N4 would literally be the number of carbons. N1 would literally be the number of hydrogens or halogens, right? And or if they're both hydrogens and halogens, then it would be both, right? And N3 would be the number of nitrogen a lot of times, right? So let's see if we can go back to our formula for the previous compound that we looked at and see if we can work out what the DBE is, and explain what kind of information it gives us. All right, so that is the compound that we posited, and this is the molecular formula. All right, so here I have an example of us working out the DBE for the previous compound with the molecular formula seen here. Right, so 1 plus N4, so that is the number of carbons. So the number of carbons is 7 minus N1 minus N3 divided by 2. So we don't have any N3, we don't have any nitrogens. So we're looking for the N1s, which is the number of monovalent atoms. That is the number of hydrogens and halogens. So here we have 7 hydrogens and 1 halogen. So that's a total of 8, right? Monovalent atoms. So we just plug in 8 here. So that is 7 plus 1, 8. And, we work that out to be 4. So what that number means is that you have 4. Let's just go back to what it stands for, DBE. It stands for double bond equivalence or degrees of unsaturation. So we have calculated 4 here, which means in this particular instance that we have 3 double bonds and 1 ring, right? So 4 could mean, for example, 2 rings and 2 double bonds. So we're not going to know. Once we get a number, we don't know. In what we have here is 3 rings. Sorry, 1 ring. 1 ring and 3 double bonds. Right? So 4 could also mean 4 double bonds, or it could mean 4 rings, right? So the number that we get, the number of double bond equivalents, means either rings or double bonds. It could have a mixture of both, but at the end of the day, that number should be equal to 4. All right, so it could be 3 rings and 1 double bond, for example, right? At the end of the day, 3 plus 1 is equal to 4, 1 plus 3 is equal to 4, 2 plus 2 is equal to 4. And as I said, it could be 4 rings, right? As well as it could be 4 double bonds, right? So that's what it means. And it's a very important tool to have, because if we're dealing with an unknown here, and again, anytime we calculate the DBE for benzene or benzene type structures, then it will be 4, right? So if you're given a molecular formula as we saw here, and the first thing that you need to do is to work out the DBE, right? And if you get 4, that further confirms that, along with the value of the chemical shift, that you have a benzene type situation going on, right? So an important set of calculation here. And so finally, we have a review question. Deduce the identity of compound A with the data provided. Explain your assignments, right? So first, you use the molecular formula, calculate your DBE, use your IR data, right? And use your proton data seen here. And try it. So that is where we end for today. And thank you so much for watching. Try these questions, try the examples, go over them repeatedly so that you can increase your knowledge and increase your experience.